ಹಲೋ, ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ಐ ಆಮ್ ಪ್ರಭಾಕರ್ ಹಂಪಿಹೊಳಿ, ಪ್ರೊಫೆಸರ್ PR ಹಂಪಿಹೊಳಿ, Head Department of Mathematics, KLS, Gokti Institute of Technology, Belgavi. We have come to the fourth lecture of Fourier transform, Module 3 of third semester Engineering Mathematics, 18-31. So, dear students, in all these three previous classes, you are used to the definitions of Fourier transforms and how to find given f of x to f bar s. Let me not go to the previous classes notes, and whatever the definitions we are using, they will be repeated. I had completed 3 examples, and in the last class I introduced the third example, but let me repeat that example. And as I told, please be ready with your pen and pad. Let us have blackboard effect, and more you get used to the symbols, better you learn mathematics. Here we go. Are you ready with pen and pad? So, example number 4. Example number 4. Again, we are finding the Fourier transform of find the Fourier transform of a function f of x which has got 2 parts. One is 1 minus mod x and one is 0. This is under the category of mod x less than or equal to 1. So this format in the previous examples also you have observed, and this is outside the range mod x greater than 1. And there is a deduction part also here. That deduction part, and hence show that, hence deduce that, hence evaluate, anything you can write, hence deduce that some particular type of integrations we prove which is not possible by our usual methods or usual previous knowledge. Sin square t by t square, hope you can read, this is sin square t by t square dt. Amazingly beautiful value pi by 2 we get. As you have seen in the previous classes, first we find the corresponding f bar s function, s function for this, s domain function. So that will be covering this part. To find the remaining part, you have to consider the inverse Fourier transform. I am repeating, first direct Fourier transform definition you use to find f bar s. Always for deduction part, use inverse Fourier transform. Here we start the solution part. So can you recall the definition of Fourier transform? Fourier transform of a function f of x is nothing but minus to plus infinity. This is known as weight function, kernel of a function. If you go on changing this, you will go on getting different transforms. You can go on changing this and these limits. You can create your own transforms. E raised to isx f of x dx. Now before I write the values of f of x, let me try to draw this function. So I'll take x axis, y axis. This is our y axis. Let me take x axis. So how this function behaves? So from minus infinity, this is our x-axis, can draw properly. This is our y-axis. From minus infinity to minus 1 to plus 1, and 1 to infinity. Again we require this 0 here. This part is mod x less than or equal to 1 part. Outside this range, it is mod x greater than 1, mod x greater than 1, mod x greater than 1. So again, here in this part, we have 1 minus mod x in the range mod x less than or equal to 1. Now here again there are 2 parts. Minus 1 to 0, this is negative part, and 0 to 1, this is positive part. What is the value of mod x in negative part? Value of mod x is minus x whenever x is negative. So this I have to replace it by minus x in this part. And whenever x is positive, this is plus x. So here I have to write 0 outside the range. Here it is 1 minus of minus x. So I have to write here minus x, because the value of mod x is negative whenever it is negative value. X is in the negative range and it is positive whenever it is in the positive range. So if I write in the negative range 1 minus of minus x, this becomes 1 plus x, and this becomes 1 minus x, this becomes 0. So if I draw these parts, this starts looking like this. With little effort you can draw 0 here, and if you put x equal to minus 1, this part, if you put x equal to 0, some height 1, you have to join these two. Similarly, if you put x equal to 0 here, the same thing, and x equal to 1, it becomes 0, it comes like this, afterwards 0. So let me not go in detail of this. So the function given us is, this whole thing is f of x, has got 1, 2, 3, 4 parts. That means this integration has to be divided into 4 parts, from minus to plus infinity. So here we go. So Fourier transform f of x, it looks like this now. Fourier transform of the given function f of x, which becomes some s function. This integration has to be broken into 4 parts in this fashion: minus infinity to minus 1, first part. Let me write these 4 parts: minus infinity to minus 1, minus 1 to 0, because here it is minus 1 to 0, then 0 to 1, then 0 to 1, then 1 to infinity, and add all these, and write the respective f of x values, keeping e raised to ix as it is. So what are the respective f of x values? In this range means in this range 0. See, minus infinity to minus 1, 0. That means here I have to write 0. Let me write that 0 here. Similarly, the last part is 0, which is 1 to infinity. And here, when I come here, minus 1 to 0, f of x is 1 plus x. So if f of x is 1 plus x, I have to replace this by 1 plus x and write here. So e raised to isx 1 plus x dx. It is better if I write this left side. Similarly, this part becomes 1 minus x here in the range 0 to 1. So shall I write 1 minus x is the value of f of x into e raised to isx dx. Now remains is integration. So when I integrate this part, first and last integration 0. So integration by general rule of integration by parts, slowly we shall write. So we should be little careful. F bar s, this is 0, minus 1 to 0 part. First 1 plus x as it is, then integration part, alternatively plus minus. 1 plus x becomes differentiation of this with respect to x becomes 1. So when this becomes constant, next terms need not be written. This we are integrating. First what I wrote, any function, polynomial function x square, first you should start keeping as it is, then go on differentiating. E raised to isx, once again I will tell you what is the integration of e raised to 2x. This whatever is behind x, that 2 is a constant, that constant comes down. Instead of 2 here, e raised to isx means is constant. Is will come down here. So So that is e raised to isx divided by is. With respect to x, remaining part is a constant. Once again if I integrate, once again is will come down into is once again. So that same type of treatments are there in almost all the examples. Let me tell you once again what we did. Differentiation part 1 plus x, again differentiate. So first we keep as it is, then differentiate. Integration start directly, e raised to isx by is, again integrate, one more is will come down. This x equal to minus 1 to 0. Next one, instead of 1 plus x, here 1 minus x is there, that is the only difference. So that this plus, only 1 minus x is the difference, e raised to isx upon is, just like previous part, minus of, be careful here, this differentiation is not plus 1, this differentiation is minus 1. So differentiation in one bracket you go on writing, see like this, differentiation in one bracket, integration in one floor bracket you go on writing. So that here differentiation is over, integration this floor bracket, e raised to isx upon I square, s square. So this range is 0 to 1, without fail proper range you have to write. So now substitution carefully, everywhere, wherever x is there, you have to go on substituting. First suppose this part, upper limit 0 minus lower limit minus 1. Here also 0 first, then minus 1. Start. Upper limit 0, 1 plus 0, 1, e raised to 0, 1. So upper limit is over. This common I will write. This is common because there is no x here. Upper limit is over, x equal to 0. This upper limit I am talking. X equal to 0. So when I take this x equal to 0 here, 0 here, 0 here. 1 plus 0, 1, e raised to 0, 1. Upper limit over means immediately what you should do? Minus of lower limit. What is lower limit? Minus 1. So wherever x is there, put minus 1. 1 minus 1, this becomes 0. So lower limit is 0. So this part is over. Here you come. So here if you see, I square is minus 1. Never forget that. Every time we'll be using this I square equal to minus 1. This minus 1, that is I square equal to minus 1, this minus 1 and this minus 1 together make it plus. So first let us write this as this becomes plus sign. Now x equal to 0, upper limit, denominator let us keep as it is, because already I square is minus 1 is consumed here, e raised to 0, 1, minus the lower limit, okay, which is x equal to minus 1, e raised to minus is. So what we did? Upper limit minus lower limit, we went on substituting. So this first part is over. This entire first part is over, that is minus 1 to 0 part is over. So this shall I write in this fashion. Now next part, you should be little careful. So when I come to this next part means this part. First let me write plus. What are the upper limits here? 0 to minus 1. The previous case it was 0 to 1. The previous case it is, let me see once again. See, it is, in this case it is 0 to 1. Upper limit is 1, lower limit is 0. Shall we start writing the second term? This term, okay. Now this term is already written. This term I am writing. First, wherever x is there, x equal to 1. X equal to 1 when you substitute here 0. So that this is I will write common. Upper limit 1 minus 1 minus 1 0 minus of the lower limit. Again x equal to 0 here, x equal to 0 here, x equal to 0 here, x equal to 0 here. So x equal to 0 1 here, x equal to 0 e raised to 0 1 here. So this part is over. Now come to this part. How many minus signs are there? 1, 2 and this is also minus 1. 3 minus signs make it minus. Upper limit 1 e raised to is. So that this s square I will write common. Upper limit x equal to 1, that means e raised to is minus the lower limit. Wherever x is there 0, e raised to 0 1. So we are done with all the limits. Now in this part x should not remain. That is fundamental. Every time I am telling x should not remain. If x remains, big 0. Now we shall see that some parts are getting cancelled. Can you see that? This is 1 by is and this is minus 1 by is. These two get cancelled. So next part, what all remain, let us see. So all s square parts are remaining. That is s square. So second terms are s square parts. These second terms are s square parts. So let us simplify s square part. So first of all, let me write 1 as it is. 1 as it is. Minus e raised to is and minus e raised to minus is. See here there is 1 by s square and minus of minus plus. Here also there is 1 minus of minus plus 1. So shall I write it as 2? Thank you. So 2. Then these exponential terms both are negative, minus and minus. One is e raised to plus is, one is e raised to minus is. So that 2 minus e raised to is plus e raised to minus is. So let me write in this fashion. 2 by s square minus, and we recall this e raised to I theta plus e raised to minus I theta divided by 2 is cos theta. So that whenever there is a plus sign here, we think of cos. To bring cos, you have to divide by 2. So that I have to divide this by 2. E raised to is plus e raised to minus is. This divided by 2 will be extra. This divided by 2 will be extra to make it cos theta pattern. So I have to multiply this to compensate that. So now 1 by s square as it is. This 1 by s square as it is. This s square we should not forget. Now almost we are in the final form of Fourier transform s function. So 2 by s square as it is minus this part is a cos function. Instead of cos theta, it is cos s. So that remaining part I have to write as it is 2 by s square cos s. This can be considered as answer, but further if I proceed, if I take 2 common, s square common, it becomes more compact form. S square common, 2 common, 1 minus cos s. This also can be answer to this. Or we know that 1 minus cos theta is 2 sin square theta by 2. This also can be answer. So 1 minus cos s can be 2 sin square theta by 2. So now if I write that, use this value, how it looks like this. 2 as it is, this square bracket becomes again 2 sin square s by 2 divided by s square as it is. So 2 into 2 4. Finally I can write the answer as f bar s Fourier transform of the given function is 4 times sin square s by 2 whole divided by s square. Let us note this. f bar s function, because in the deduction part we will have to use this. This is the first answer. Now let me come to the deduction part, which is asked in the example. Okay, let me come in the deduction part. Okay, in this deduction part, so this was s square. In this deduction part, carefully see what you are asked. Yes. See what you are asked. Here it is. What is the value of sine square t by t square? Almost a similar thing we got. To find the deduction part, always consider first inverse transform. Inverse Fourier transform. So can you recall the definition of inverse Fourier transform? Can you recall the definition of inverse Fourier transform? Let us recall. Consider inverse, sorry, so let me write once again. So this was this we have noted as the answer. Now consider inverse Fourier transform. Consider inverse Fourier transform of f bar s. So what will get? Fourier inverse of f bar s. So back we will get x function, which is 1 by 2 pi minus 2 plus infinity f bar s into e raised to minus isx dx. So what we considered? Inverse Fourier transform. Now this part is same thing as this part. So we have to copy paste this entire thing here. So shall we do that? That is equal to 1 by 2 pi minus 2 plus infinity 1 by 2 pi minus 2 plus infinity 4 by sine square s by 2. I am just writing the value of f bar s whole divided by s square into e raised to minus isx dx as it is. So now there is a small change you have to do. Has anybody noticed? This is not x, this is s. I heard somebody telling me this. This is not x, this is s. Now this 4 you can adjust here. So this 2 pi will transfer here, 2 pi f of x minus 2 plus infinity sine square s by 2. This 4 if I transfer here, this is s square by 4 I should write, or s by 2 whole square, or I can write it as so this 4 is adjusted like this, s square remains as it is, and here you see I'll write e raised to minus isx as it is. But this 2 pi transfer to f of x, 2 pi into f of x. Now you can very easily guess. Okay, what was f of x? What was f of x given? What was f of x given? F of x was given like this. F of x was given like this. I'll recall here only. In the range mod x less than or equal to 1. So if I put x equal to 0 here, f of 0 is 1 minus 0 becomes 1. So now I'll choose x equal to 0 to bring it to the format of whatever we are deduction asked. So choosing is important. You want this, it is asked, this part is asked. So this is ds. So once again I am telling, in the deduction part in the question, this part is asked. So this you want to make it 1. If at all you want to make it 1, this should become e raised to 0. So whatever in the right hand side also variable should be there, left hand side also variable should be there. You cannot select s, because the right hand side s is not there, s is not there. So both sides x is there. So you can select x as 0, e raised to 0, 1, f of 0 is also 1. So if I do that, choose properly, choose x equal to 0. So minus 2 plus infinity sine square s by 2 by s by 2 whole square into 1 ds equal to 2 pi into 1 f of 0, or 2 pi into 1, which is 2 pi. Now remains is you have to bring into the standard format. This part you can substitute it as some variable t or z or something. So let this be, let s by 2 be t. That means what? ds equal to 2 dt. So this ds value I have to substitute it as 2 dt. Also, whenever I am changing s to 0 to minus 2 plus infinity, t also becomes minus 2 plus infinity. So in terms of t, if I transform this, what I will get? So minus 2 plus infinity remains as it is. Sine square s by 2 I have written it as t. So s by 2 I have written it as t. This becomes 2 dt. So this is 2 pi as it is. 2 is getting cancelled. 2 is getting cancelled. Now this becomes an even function, because it is a square function, sine square t is an even function. So that I will consider this whole integrand becomes an even function. Why it is even? If we change t to minus t, the function will not change. It remains as sine square t by t square. By changing t to minus t, wherever t is there, if the function does not change, then it is even function. If it is even function, 2 times 0 to infinity it becomes. So next case is that, and that ends this evaluation process, which is 2 times 0 to infinity sine square t by t square dt, because this 2 is getting cancelled, this 2 is getting cancelled, equal to pi. Final answer, 0 to infinity sine square t by t square dt is pi by 2, because this 2 is transferred this side. Now instead of t you write any variable, z you can write, x you can write. We want the answer in terms of x. Then in the last case, in the last example also you have written it, change x to nice. 1 minute. Change s to x. So this here s to x if we change, therefore final answer becomes 0 to infinity sine square x by x square dx. If you recall that, without squaring also this part was sin x by x dx also was pi by 2. Sin square x by x square dx also pi by 2. Amazing results. So here I have completed the example number 4. Let me go to the next example, which is example number 5. Example number 5 is a little different. So let me explain that. through this already ready material. This was example 3. Example 4. Now come to example 5. In example 5, see, find the complex Fourier transform of this. Also deduce that this becomes self-reciprocal. Let us go on doing the example and let us see what is the meaning of self-reciprocal also. There are very one or two self-reciprocal examples for examination point of view. Dear students, these are the very important examples. You have to go on repeating these examples. Similar type of examples are always asked. First, find Fourier transform definition. Minus to plus infinity e raised to x f of x dx. Now f of x is given as e raised to minus a square x square. Substitute here. So now I'll take this e raised to minus a square x square common. See this. If I combine these two, this looks like this, e raised to minus a square x square plus isx. From this, if I take minus a square common, x square, this becomes minus, divided by a square you will get. That is done here. So from this, minus a square common is taken. Now this is just like a square. This part is a square minus 2ab. How do you write it? X square minus 2 times a into b. B part is remaining part. Already is is there. Carefully. A square is there, but to compensate this 2 I have to write 2ab. What I am going to do is, to make it a perfect square, first I will write b square part. Square of this, I square, s square, 2a square whole square, that is 4a raised to 4. B square part. This is a square minus 2ab. A is this, b is this part, square of this. So b square, whatever you have added, you have subtracted. This whole minus a square is common to the whole range. Once again, first minus a square taken common, only a square minus 2ab term is there, a square minus 2ab term. How this is adjusted? Minus 2 times x into is, here also 2 written. So is by 2a square is b, square of this is added, square of this is subtracted. Now what happens is, this whole thing acts as this part. This part acts as a minus b whole square, where a is x and b is this part, a minus b whole square. This part you can extract outside like this. While extracting outside, keep in mind that I square is minus 1. Here one minus sign, here one minus sign, here one minus sign, 3 minus signs. Totally e raised to this will come out. I am writing here first this marked part perfect square, x minus this square, a minus b whole square, e raised to minus a square into a minus b whole square. This part is separated. Okay, this part is separated, e raised to minus a square. So a square and a raised to 4, a square will remain in the denominator, 4 as it is, s square as it is. Only thing is minus, here minus, 3 minus signs. You can observe that this has no x term. You can keep it outside also, which I have done in the next. E raised to minus s square by 4a square. Now remains is this. Now what we do is, this whole bracket we keep it as some t. That is a into this part. Before squaring part we make it t. So except x remaining are constant, a dx equal to dt, or a dx equal to dt, or a this side dx equal to dt by a. Here this I have to substitute dt by a. And always whenever you substitute like this, limits are not changing, minus infinity here, minus infinity here, infinity here, infinity here. So can you write in terms of t now? For time being, outside as it is, range as it is, this will become, this whatever I have marked will become t e raised to minus t square dt by a. A you can take out. A you can take out. So I have taken a out. And this is a standard value. You have to remember, please, this comes under beta gamma functions. You might have learnt in your previous first year classes. This becomes exactly root pi. If it is 0 to infinity, this becomes root pi by 2. Fantastic answer. What a nice answer using beta gamma functions. Root pi you will get. This is exactly whatever I have marked here. Root pi you should replace root pi by a. Root pi by a into e raised to minus a square by 4a square. This is the answer to the Fourier transform. Now if at all I have to choose, show that something is reciprocal, choose a square equal to half. When you choose a square equal to half, e raised to minus a square x square becomes same thing as e raised to minus a square by 2. That is what I am trying to tell is this. See, when I choose a square equal to half, here also, what it becomes? E raised to minus x square by 2. And in the answer also, if I choose a square equal to half, this becomes e raised to minus s square by 2. So this remains the same, structure remains the same, x becomes s, something multiplied, some constant here, that is root 2 pi. So that same thing you can get means it is reciprocal, that is the meaning. So with this we will go to the next example. Before that, let me do this example once again quickly. Example 5. Show that this part is reciprocal at last using this. So we have chosen a square equal to half. For Fourier transform definition, put f of x equal to e raised to minus x square. Put f of x equal to e raised to minus x square by 2. Then try to make it a perfect square using this. We have made a perfect square here by combining both because base is same. If you multiply these two, you will get in this fashion. So taking minus a square common, using a square minus 2ab plus b square format, add b square term, subtract b square term. Whichever is not x, you take it outside in the next case. This is a minus b whole square, like this. A minus b whole square, a square as it is. This part is extracted outside like this. Now convert in terms of t. Forget this square part. Inside square part a is there, this small bracket is there, that part is t. A dx becomes dt, dx becomes dt by a. In terms of t, it looks like this. This is a standard root pi value, root pi upon a into this. This becomes the one set of answer. Here if you select, okay, here if you select, this is the one set of answer. But now you have to show that x square by 2 is self-reciprocal. For that you have to select a square equal to half. Naturally, x square by 2 you want, no? A square equal to half. A square equal to half. By selecting that, what amazing thing happens here is, simply x square by 2 becomes a square by 2. Just multiplied by root 2 pi. Same structure you will get. Okay. That's why it is reciprocal. Let us see the next example. Find the Fourier transform of modulus of e raised to minus mod x, and hence show that this. Now what is the mod x curve? Mod x is positive in the range. Mod x is plus x in the positive range. Mod x is minus x. So for the purpose of knowledge, I wrote minus mod x curve here. This comes down. Mod x is negative. So just ignore this part. Now f of x is e raised to minus mod x. So in the positive range, the value is plus x. So I have to write the value of this as x. So totally it becomes e raised to minus x in 0 to infinity range. In 0 to infinity range. 0 to infinity range. This value is e raised to, here I have to write it as x. Now there is a standard formula for such thing, which I will write now here. E raised to alpha x sine beta x, integration value is e raised to alpha x divided by alpha square plus beta square into bracket alpha sine minus beta cos. Okay. So if I use this, alpha is minus 1 sine sx minus beta is s here. Alpha is minus 1, beta is s. So that alpha sine sx minus beta cos sx e raised to alpha x as it is, e raised to minus x upon minus 1 square plus s square. So using this formula, similarly cos beta x formula is also there. When we come across that, I will tell. So once again, let me write this e raised to alpha x. Okay. For few students, I will write this e raised to alpha x formula for you once again. E raised to alpha x sine beta x formula e raised to alpha x sine beta x formula, write down properly, e raised to alpha x divided by alpha square plus beta square into alpha sine minus beta cos. Okay, in the previous case, alpha has become minus 1 and beta has become s. Just replace that. Now let me go to the example. Using that formula, once you write that, you start getting like this. So here wherever x is there, you have to substitute infinities and 0. But upper limit e raised to minus infinity tends to 0, upper limit becomes 0. Minus the lower limit. X equal to 0, 1. X equal to 0, this becomes 0. Minus cos 0 has become 1. So only minus of minus s remains. So hence s by 1 plus s square. Denominator there is no x, remains as it is. F bar s of s is s by 1 plus s square. So that Fourier series of e raised to minus mod x is s by 1 plus s square. What we did quickly? Given a function, first we wrote Fourier sine transform. Find the Fourier sine transform. So first time we are doing the example of Fourier sine transform. For sine transform, the definition is 0 to infinity, not minus to plus infinity. Okay. To the function, instead of e raised to isx, we are multiplying by sin sx. That you should remember. So function is e raised to, here because 0 to infinity is positive, x remains as it is, e raised to minus x. Using the formula, we wrote the answer of this is integration answer. Wherever x is there, if you put infinity, e raised to minus infinity has become 0. Wherever x is there, if you put lower limit, minus of the lower limit, x equal to 0, x equal to 0, x equal to 0, x equal to 0, e raised to 0, 1, sin 0, 0. So minus s remains, s by 1 plus s square, this becomes our answer. Now come to the evaluation part. You are used to evaluation part. For evaluation, if sine transform is there, inverse sine transform you should take. Inverse Fourier sine transform definition, 2 by pi. This is inverse Fourier sine definition. 2 by pi 0 to infinity f bar s of s. This s denotes, suffix s denotes sine sx, again ds. Now what we are doing? This will give us back f of x. But f of x is basically e raised to minus, f of x is basically e raised to minus mod x. 2 by pi as it is, 0 to infinity as it is. This f bar s value, okay, is brought here. S by 1 plus s square you write here. So now this 2 by pi if you transfer this side, okay, what happens? 2 by pi if you transfer this side, 2 by pi means pi by 2 into e raised to minus mod x. Okay. So now, first of all, we select wherever x is there, you put m here and m here. Can you see that? M here and m here. So this becomes m, this becomes m. Simultaneously, wherever s is there, you make it, wherever s is there, you make it x. So x by 1 plus x square. So this becomes x, this has become m dx. So only two changes now. X has become m now, and wherever s is there, you convert it to x, so that we get the desired result. So here we stop today. We have done some few examples. In every example, wherever evaluation part is there, we are considering inverse Fourier transform or inverse Fourier sine transform, so that if you remember definitions and same type of integrations with a little concentration, you will be able to do all these things. So till the next class, I take your leave. Bye, be safe, and don't take any liberty, don't relax still the pandemic is not completely over. Take care, bye.